Hello. So I'm here with the gnomes today because it's been really lonely in the lab by myself. And this little gnome, who's a rocket ship on his off time, he and I measured out the salicylic acid. Remember the scales? And scales are very touchy because they're very lonely. So we measured out 3.164 grams. If you don't believe us, we'll see if we can do it right this time. Can you see? Maybe? Maybe not. There we go. 3.164 grams. All right, I'll write it down. And we're going to pause. Maybe. All right. Well, here's our next note. He's going to help me. We have put the salicylic acid into our flask, and perhaps you'll be able to see. And now we have to hold our breath because the hoods are off. We're going to measure out 5 milliliters. A long time to hold our breath. Oh, I had a day rip. That stinks. All right. So, you're going to trust me on this. I know how to read this. And 5.20. Got it? 5.20. We got it. Add the catalyst. Count the 6 drops. It's not just a catalyst. It's never just a catalyst. And now we start our timer for 15 minutes. And normally during this time, this is when you do your calculations. Now I'm going to teach you how to read that chemical equation. All right. So let's look at the board. We got the monkey in the middle and our teaching gnome here. And I was like, you know what? You guys have been doing so amazing. I'm going to give you a little quick organic chemistry lesson. So molecules, there's a shorthand way of drawing the really big molecules. And it's every corner is a carbon. You may have heard me talk about this. And so it's just a shorthand thing where rather than writing them all in, we just show it like that. So this is a carbon, 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 carbon. So we have 6 in a hexagon, 7, 8, 9. So we have 9 carbons. Now every carbon makes how many bonds? This is one of those big lessons from Chem 104 and Chem 151. Chem 104 says it 4. It makes 4 bonds. So this carbon has a double bond on this side and a single. It's actually a 1.5 on each side, so that's 3. So there's going to be a hydrogen there. And this one, 1, 2, 3, so it has a hydrogen to make the 4th bond. Hydrogen, hydrogen. This one up here already has 3, 4, and this one already has 4. So we don't show all the hydrogens because anybody with some chemistry should be able to figure it out. So I now have 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. And then I count my oxygens. 1, 2, 3, 4. 4 oxygens. It's a lot of oxygens. All right, but it's got a lot of carbons too. So what happened in this chemical reaction? So you can do that also for the salicylic acid and the acetic anhydride. So what happened is the salicylic acid, which is what we measured, the solid there, and the acetic anhydride, which means without water, anhydrides are extremely reactive. And so they do a chemical reaction, organic chemistry. And so this OH pops up and this piece pops on. Oh, you know what? Your teacher forgot to draw the bonded O there. And then this OH, it's going to hook up right there. And this is going to hook up right there. And we get acetylsalicylic acid, which is aspirin. All right, we're going to pause again. Let's see if we can do the pause. All right, I'm back. And it's been 15 minutes. The gnome watching the clock told me so. So, our sample, it all dissolved as it was in the warm water. This is the exciting part. Are you ready? Are you ready? We're going to add some ice cold water. Did you see that? We're making crystals. We got to precipitate. The reaction was happening, and we add the cold water. Aspirin is not water soluble. There's too many carbons there. And so we just allow it to keep forming. The crystals are going to form in the ice cold water. I'm not going to show you the ice because the water here, since it's not run, it's accumulated all this gunk and it comes out brown. It's a little worrisome. Makes me wonder if any of these buildings will even exist after a year or two. But we don't have to worry. We're in this make-believe land. Let's go back while we wait our 5 minutes and finish these. So, let's count our carbons. 6 in the hexagon plus 7. So this is C7. Hydrogens. Yeah, you can't see me. So remember, this is going to have a hydrogen, because we have to make our 4 bonds. Hydrogen, 1, 2, 3, 4, and then 5, 6. So we have 6 hydrogens. It's going to pick up some of those hydrogens to get to 8 and some of those carbons, and we just have 3 oxygens. All right. Acetic anhydride, we have a carbon, 4 carbons, 3 oxygens. We show the oxygens last because they're the most electronegative, and 6 hydrogens. And then the acetic acid is just 2 carbons, 4 hydrogens, 2 oxygens. So does it all add up? Well, 7 plus 4 is 11. 9 plus 2, we have 11 carbons. 6 plus 6 is 12 hydrogens. 8 plus 4 is 12 hydrogens. And then 3 plus 3 is 6. 4 plus 2, so we just rearranged. It's a kind of exchange reaction in organic chemistry. So, what normally students would be doing, except I keep hitting pause, is you're going to do the math. So, from the amount that we started with, what was it, 3.164 grams of the salicylic acid, using this and your handy-dandy periodic table, you can change its moles, a 1 mole to 1 mole ratio for the aspirin, and then we want to know how many grams of aspirin are possible. And then you're going to do the same thing with the acetic anhydride, except that we started with 5.2, it was actually 5.22 milliliters. Now we have to change it to grams, so we need the density. So milliliters to grams, handy-dandy periodic table, grams to moles, mole to mole ratio is just 1 to 1. And again, we solve for our grams of aspirin. Now, only one of them is going to be right. It's the limiting reactant. The smaller one is always going to limit you. So we pick the smaller one, we give it a big hug, and we cross the other one out. If you're doing this right, salicylic acid should give you the smaller mass. This should be our limiting reactant. The mass that we're going to end up with, well, the aspirin's a little bit bigger than the salicylic acid, so it should come out close to 4 grams. Maybe a little bit less when you do your math. I don't know. I didn't do my math because I'm doing the experiment. That's your job. All right, let's see how it is. How did we do? Oh, wow, look at all that. So we're going to do something really cool now. We're going to do suction filtration. And there it is. We turn on the vacuum, that noise you hear, and we dump it in. And look, it's pulling down the water, because there's a vacuum here, pulling all the air out, and we'll transfer it all. All right, we do our best. Maybe we get all of it, maybe we don't. There's always room for losing some crystals. I'm good with that. So we'll let it suction, pull out some of the water, and then I'm going to transfer all my crystals so we can turn off our vacuum. We'll be back to the vacuum because we're going to recrystallize it. Let's make it even better than it was. There's some persistent crystals on here. Let's see what we got. My handy dandy gnome. Yeah, we'll just scrape as many crystals as we can off. Okay. But you know what? There were some crystals left in the flask. There's some crystals left here. At least I didn't spill any, right? Oh, there's even crystals left everywhere. Let's see. So, you know, I didn't do so great on that last lab. And, yeah. I'll get a standing ovation this time. Now, we're not going to add water to re-solidify it and recrystallize. We're going to add ethanol. Because ethanol has carbons and hydrogens and oxygens. So these guys are friends. And then we'll warm it up, dissolve all of it, and then I crystallize it again. All right, I'm going to pause you. Well, you guys do your math, so you can pause me too. You ready? It all dissolved in the ethanol. We had to warm it up a little bit. So you can see it all dissolved, and then we add the ice cold water, and we got crystals again. It's really exciting. So we'll chill it on ice for 5 minutes. We'll suction filter it again, and then we'll dry it and see how we did. All right, keep doing your math. I'll be right back. I'm going to clean up while we wait. Maybe. So, take it out, give it a good swirl, turn on our vacuum, and the crystals this time are much finer. Here's the real question. Well, I believe it is a post-lab question. Oh, I don't know if you can see that. My solution down there is kind of cloudy. It's like some of my crystals I lost. That's alright. The gnomes told me. Everything's okay. Alright. And transfer. And then we let it sit for 5-10 minutes. And then we're going to steam dry it. We're going to get a mask first. Just to make sure. Alright. Put you on pause again. You guys are doing your math. Crystals went through the filter paper. Crystals are still on the filter paper. Even lost a little piece of crystal when we were transferring it to get the mass. The gnome back there fell asleep. Alright. And then, as I started heating it, it started dissolving. So, I got out the heat lamp. We're going to do it that way. Might be a little safer. Alright. Then I took my wee sample and I dissolved it in ethanol. Because again, it's not water soluble. Just too many carbons. Oxygens. Yeah, there's a lot of oxygens too. It just doesn't like water. And this is fascinating. We added this, the yellow. And then we add some water, and it's not going to fit in our wee beaker. And then we're going to go do the spectrophotometry thing. Alright, remember the step before? We're out here with the spectrophotometer. Here's our gnome. Picked a different one this time. But you know what's really interesting? They're all set at 525, which is what I need today. Every single one of them. Even the one I used last time. And I'm pretty sure it wasn't supposed to be at 525 last time. I'm pretty sure nobody else has been here. Which is really interesting. Maybe that was my mistake last time. Anyway, I'm really excited because this is supposed to be as clear, very clear, and it's looking very clear. So I zeroed it already with water. I'm putting it in. Oh my goodness, we did pretty good. It's like, can you even see? Maybe. It's way down. It hardly absorbed anything at all. 0.035. I zeroed another spectrophotometer just to check. Should we see if we get the same answer? Gnome's gonna come along. Be right back.
Oh, this one's even better.
Let's go with this one.
0.0, so 0.028. Got it?
All right. Now, let's pause. We're gonna do melting point while it's still drying and see if we get the melting point of pure aspirin. All right, keep doing your math. Before we lose our knock, getting a good look at the aspirin and our mass. 1.618. Oh, sorry, 1.633. It's all right. It's better than 50%, right? So it's passing grade. Gnome over there was doing melting point. He got 126. It was actually a range, 125 to 128. It's pretty good. Melting point of aspirin is 135. So we're a little bit low, but the melting point of salicylic acid, the starting point, is 160, 159. So we definitely made something. Question is, how pure is it? And that's what you're going to figure out. Definitely should try it, because we're going to throw it out anyway. All right, good luck on the lab. The post-lab analysis is where the points are. So many blessings. I hope you all had a really awesome Thanksgiving. Much gratitude for this whole term. Thank you so much for your patience with me, and I hope to see you all soon. Bye-bye.